thank you all for being here today. Thank you, Dr. Bieber, for coming in. You know, I recently defended. I'm still processing in it, but thank you all. This is part of the dissertation, the PhD dissertation that I defended last week. And I am proud to say this is the fun part of the presentation. What we will talk about is pedestrian GraphSLAM using smartphone-based PDR in indoor environments. The two main keywords that pop up here is GraphSLAM, which is graph, simultaneous localization and mapping, and PDR, which is Pedestrian Dead-Reckoning. We will talk about these two in a little bit more detail in the next couple of slides, in case you haven't crossed paths with any of them before, which I myself haven't like 2 years ago. So we'll do that first, and then we will go to some of the contributions that we did in the work. In the presentation, I will briefly give a background about GraphSLAM and PDR, and then there are two main parts. The first part is how we use smartphone sensors for what we call pedestrian indoors simultaneous localization and mapping. The second part would be how to share data from different smartphones to improve the GraphSLAM approach using Bluetooth measurements. And then finally, I will very briefly, just one slide, talk about how we can use the trajectories for improving indoor localization, or the measurements that we get from GraphSLAM to improve indoor localization. So, the whole work started from indoor localization and mapping. As you all know, we have so many emerging location-based applications and services that require accurate estimates of indoor positions, people inside buildings. What I would specifically like to highlight is the E911 enhanced 911 services, which based on the development or let's say the proliferation of smartphones within the last years, most of the 911 calls now originate from mobile phones. Most of the phones are inside buildings, and so the FCC is pushing for more accurate location estimates. So when someone calls 911, they want the providers to provide location estimates, not just at where he is in terms of a building or an address, but where he is inside the building. So at a specific room or an apartment or suite. So we need very high, accurate indoor measurements. On the other hand, let's say the currently deployed positioning techniques are mostly optimized for outdoor operation. You have GPS, cell ID, different forms of time of arrival estimation. They work very good, at least a lot better outdoors. Indoors, we still have the line of sight problem. Most of them depend on they need line of sight communication. With the multipath fading inside buildings, we don't have the accurate estimates that we need. Most of the indoor positioning systems employed now depend on what we call fingerprinting, which is basically a two-stage process. So first you have, is that a question?
Yeah.
Or just yes, okay.
Just one question. So what's the typical accuracy of indoor and outdoor localization?
So GPS could record up to 5 meters of accuracy outdoors. Indoors, that's way worse. And like so the typical accuracy is for outdoors. For Wi-Fi techniques, which is the specific techniques for indoors operation, they have much better accuracy. Could go to up to 1 meter or 2 meter, but the techniques have their own challenges, and this is why it's still a problem. Because again, most of the techniques depend on fingerprinting, and fingerprinting, it's basically stage one. You have dedicated people walking through the building, recording received signal strength measurements at different points, and then creating what's like an RF map. And then later on, when a user inside the building wants to know where he is, he collects his own RS measurements at a point and then compares it to the map, and then we get an estimate of where he is. The main problem with this is, first of all, the RF maps change. Walking people by, changing furniture, anything inside the building. It's dynamic. They have to be updated every once in a while. They depend on the building infrastructure. You need to have access points, whether it's Wi-Fi or any other wireless technology, and they need basic knowledge of the building. You need to know actually the map of the building first so you can build this. So they have their own set of challenges. The main idea that started the work that we're presenting here is, what if we use a user's history, movement history, instead of just where he is right now, to try and get better estimates for the location. So if you're tracking a user's movement trajectory for a specific time duration and then use the history, then you'll be able to get better estimates. So the problem comes to, we need to track the trajectories, and then we need to use the trajectories for localization. We combine here three different fields. We have indoor localization, we have what we call smartphone PDR, and then the GraphSLAM. The smartphone, I will talk briefly about each of smartphone component and the GraphSLAM component, and then we will move on to what actually the contributions that we did in the work. So, pedestrian dead-reckoning. Dead-reckoning refers to a relative position estimation technique. So instead of trying to find an absolute position of where a person is, we have the change in his position relative to a previous point. And so we can build up a history of a user's movement based on an initial point. And the change between the positions could be either a change in XY directions, or if we have a distance and an angle, then we can estimate an X position based on the previous one. Applying the reckoning for pedestrians actually started with foot-mounted sensors, something that's like in the picture, and what we call IMUs, or inertial measurement units. So basically you have a sensor that has accelerometers and gyroscopes. Accelerometers measure acceleration, which can give us an indication of the change of the distance that you traveled, and gyroscopes present angular velocity, which we can use to, again, have a measurement of the direction of the user. So if we can use accelerometers and gyroscopes to get a distance, which in this case like the step, and then we use the gyroscope to get an angle, then we can basically build up a user's movement trajectory. With the smartphones everywhere, and now every smartphone in the world has an accelerometer and gyroscope in it. So the whole problem transitioned from foot-mounted sensors to smartphones. The problem here is the foot-mounted sensors are much more accurate because they're so close to the foot. So the main movement that actually generates a signal that you can detect the change from is that when you're moving, your foot goes up and down, so it creates like a cycle in the acceleration. So with the sensors very close to the foot, they will really, the accuracy of the sensor will be much higher. The phone does not provide so much accuracy. So that's one problem. And this is one of the first problem that we try to overcome in this work, the sensor from the smartphone. If we can provide an estimate of the movement trajectory at this point, we move on to what is the third, let's say, field, or the third component of the work, which is simultaneous localization and mapping. So this is a very well-established field in the robotics community. They have robots going inside buildings. They have no idea what the building is. They try to simultaneously build a map of the building and locate where they are. And they have very established techniques, either using Kalman filters or particle filters, which somehow depend, they update positions recursively based on your last point and your present point. Or they have what they call smoothing techniques, which is GraphSLAM, which basically depend on getting an estimation of the trajectory and then optimizing the trajectory as a whole, which fits or aligns with what we want to do, is use the whole movement or the history of the trajectory to detecting the location. So we try to adapt the SLAM techniques, or more precisely GraphSLAM, into the pedestrian smartphone problem. Again, doing that, we had several challenges. Number one, the sensors. So robots that do mapping somehow look like this. They have laser scanners and cameras, and you can put on all the sensors that you need on there. You can have very good measurements. Versus your phone, you only have the embedded sensors, which is the mainly accelerometer and gyroscope. You can have a magnetometer, but it's very different. So the sensors are limited in size, in number, and in their accuracy. Number two, the information about the robot, when it moves, it gets either an order from a human operator to move in that direction, or it moves autonomously, but again, the robot can have a very good estimate of its direction of movement and how long it moved, or the distance that it crossed. Versus a human operator, we don't know where the person is going. So we don't have any prior information about where he's going. So this adds another layer of complexity to the problem, which makes you doing this in robotics, I don't say a lot more easier, but less complex. The third thing is SLAM algorithms perform a lot better when the robots can detect what we can call loop closures of landmarks. So loop closures is basically when the robot knows that it has been here before. A landmark is a fixed position inside the building. So if you can detect that you have been here before, or this is a fixed position, I can use this to optimize the whole trajectory. Again, the problem is robots do this with laser scanners, and they have very, very good processing techniques for doing that. We cannot expect, unless the human operator, like the smartphone user, actually says, I have been here before, it's very hard to do that automatically on a smartphone. So what we're trying to do, yes?
On the previous Dead-Reckoning, I think you implicitly answered this, but the Dead-Reckoning, the challenge is you're starting from an initial point and your error compounds.
Yes, the drift error.
Because
yes.
you're not resetting it. And it seems in the SLAM, that reset is provided by the loop closure of the landmark, where then
there are so many other ways to do that, but yes, the robots do that mainly with loop closures of landmarks.
So then the error can be reset.
Yes, the error resets yes. And for the sensors on the foot, since they're really close to the movement, they can detect the instant that you're stopping. So they use this as what they call a zero velocity update. When your foot hits the ground, that's a zero velocity. You can use that to reset.
But it doesn't adjust your position. The error that you had, the compounding error from the Dead-Reckoning, keeps on. It's almost if you started at 1 and moved to 15, that if there was an error ellipse around that about the accuracy, it would be getting bigger along.
Yes, and I will just show right now how the error compounds, the drift errors. But yes, that's true. So the foot sensors and the robots each have their own ways of resetting the calculation of the integrals. Mainly they're just integrals. But the smartphones, it's just more complex to do that. Yes.
Here, what do you mean exactly by optimizing trajectory? I felt that you're trying to estimate the trajectory rather than optimizing.
Yes, so I'm estimating the trajectory, right? But if I have a point and I know that after 10 points I came back to here, I can use this information to adjust the whole trajectory. If I know that at this point in time I was at this point. So if my estimate is a little further than this point, I can optimize the whole trajectory to fit with the point that I know. So based on PDR information and what we know about GraphSLAM, we will move on to the first part, which is getting measurements from smartphone sensors and using that for estimating the trajectory through a GraphSLAM framework. So again, smartphones, mainly the sensors that we're using are accelerometers and gyroscopes. So these are real measurements you collected from a phone, my phone, other phones. We have volunteers in the lab. This is from an iPhone 7. We have Ted, he volunteered his phone for a lot of the measurements. And I have people walking all around the lab with the phone. Shem, Aditya left, Ursul left. Chris, he's not here, but so we did a lot of measurements around. And so the whole point now is that we have these sensors, and we want to estimate a step length and a direction for the movement, and then use that to generate the trajectory. That's the first one. So these are measurements from an accelerometer, from the phone accelerometer, in z direction, because the redirection is the maximum that you get the change in the measurement. And as you can see, the movement, the walking pattern of any person creates a cycle in the acceleration. Each peak represents a step. And so if we do a peak detection, we can know where are the steps that the user took. And then the next step is how to estimate the length of the step. Trying to avoid integration, because this is acceleration data, we need distance, you basically need to double integration. So in order to avoid that, there has been several approaches proposed in the literature about how to use the acceleration data to estimate step length. We've gone through a lot of them. We picked one that minimized the error and gave us the best results. And it basically estimates the change, the step size based on the difference between the maximum acceleration, the minimum acceleration, with a factor, and it gives us the best estimate for the step length. So based on this data, we can have an estimate of the distance the user took at each step. The next step, which is so here we avoid the drift error because we're not using the integration. The problem comes from the angle the heading detection. So this is an example of a movement trajectory. This is based on the measurements that we get from the phone, estimation for the step length, and estimation for the heading direction. And as you can, this is the true trajectory in a building in Virginia Tech, and we wouldn't say which one for security reasons. And this is what we get from using the measurements from the phone and building the trajectory, using the heading estimation and the step length estimation. And as you can see, this is what happens with the error from the heading measurement, the drift error. It grows linearly with time. You can see the trajectory rotates. Either way, sometimes it moves this way. It just, yes.
So how is the person holding the phone? Or is it
that's another issue. So the easiest, well, I don't say that. These measurements we're taking where you're holding the phone like this in your hand. We tried in the pocket. It just needs that you need to apply a rotation matrix to make it go to the rotation matrix you get from the gyroscope. And applying the rotation matrix, you can calibrate the measurements to go back to the true values. And there has been a lot of research actually in this. In PDR, if you look smartphone PDR sensors, a lot of you just estimate the changes if you hold your phone, you put it in the bag. The main idea is that if the phone is constant during the movement, where it is, it's fine. But the problem is if you're moving the phone too much, whether you're moving, you will end up with a lot of problems in the heading detection.
I'm just curious, from a hardware perspective, does the gyroscope give any weird readings, whether the phone's like this or like this? Like, for example, if I'm holding my phone straight and I do the walking, does it differ from if I'm holding the phone like this? You get different results.
The gyroscope is orientation. So
Right. Yes.
That's what determines orientation, whether or not you're moving the accelerometer.
Sure. Does the accelerometer?
Yes.
You're also using the gyroscope in a way to, slight variations I'm guessing do come on that graph, right? So my question is just the way you're holding the
It
phone,
will make a difference.
It does make a difference.
You need to adjust for it. Because the phone would see the gyroscope axes are relative to the phone.
Yes.
X, Y, and Z. So the Z wouldn't make a difference, but the X and Y would be different. So you need to adjust to account for that. That's right. So the first thing we need somehow to account for the heading error. So if this is again another example of, so this is the heading angle estimated from the gyroscope, and as you can see here, the blue, you see the blue in the blue line is what you get from the gyroscope. And if you look at the blue line, we can see that most of the heading directions inside the buildings, because of the rectangular structures of building, most of the headings are multiples of pi over 2 because of what happens inside buildings. This is very specific to buildings. And you have transitions, and then you have movement in forward directions and transitions, and the movement in the forward directions basically are multiples of pi over 2. This is an estimation, but still, the first part of it is in order to somehow overcome the drift error, the first step is to calibrate the measurements, or just snap the heading directions to the closest multiple of pi over 2. So if you look here, this is a clusters of the heading estimations that we get from the gyroscope. You can see that they're basically around 0 and pi over 2 minus pi over 2 pi, but they're rotated because of the drift error. If we calibrate the measurements, you just bring them back more closer to the true values. Just calibrating this is the first step.
So that calibration is just a rotation?
Yes, it's basically you take windows through the measurements, and when the measurements start to drift, you snap them back. Yes.
The cause of pivot is because of the desired resolution that we are in this way.
I'm sorry?
The choice of you are taking it in multiples of pi by 2. Is it because that's the resolution that we need?
It's because of two reasons. Number one, if you look at people moving inside most buildings, it's perpendicular. You have hallways and rooms, and then number two. So I am just snapping the trajectory. I am still not. I am keeping the transitions. I haven't removed the transitions. So the transitions are there, like if you're turning right or left. I haven't removed them yet. But at this point, I'm just approximating that this should be, the change is so small, so it should be this function. This is the same example after the calibration. So this was before, and this was after. And you see, it somehow rotated it back somehow, but still we're very far from the true trajectory. So here, when we go into GraphSLAM, this is where the GraphSLAM comes in point. So what we do in GraphSLAM is GraphSLAM formats the problem as a graph optimization problem. So each position presents a node in a graph, and each edge between two nodes represent the displacement or the change between two successive positions, which is a function of the step length and the heading direction. And we define an error. The error is the difference between the true displacement, which is the unknown, and the measured displacement that we get from the sensor measurements. In other words, yes?
I have one question. So, during your measurements, did you also consider walking up the stairs or?
I did, but it's not in this work. But we did that, and it's actually showed the main difference would be in the barometer. So we have another sensor in place, and the acceleration is different, but it's not on its own. It's not enough to decide that this is a chair. You have to include the barometer data. It's actually one idea to include the barometer data or the stairs as a landmark. So, in other ways, we define this error such that if the measurement is the true value, it's a zero error. And then summing all the errors over all edges, we end up with a least squares optimization problem, which can be easily solved. But the point is we come back to loop closures or landmarks. Loop closures and landmarks, if they are detected, they are inserted into the problem as like a virtual node. That you know that this place is this point. I know the measurement. And this is what makes it optimizing based on the constraint provided by the loop closure or the landmark. The one last thing is, in order to do that, we need a covariance matrices for the error. So we have a pretty standard model for the step length. It's a Gaussian model. We have a variance. The heading direction is not that easy to have a model for it. So we added what we call a pre-processing detection approach. This is what I've been talking for, which is instead of assuming that the person can walk anywhere, or that the angle theta could have any value, you quantize the value. So it could be 1 of 8 in this approach. So you either move in 4 perpendicular directions or in 45 degrees. Which, if you're trying to find a person's if you follow the movement of people inside a building, and if you're trying to localize over a room, the angles smaller than 45 degrees wouldn't really make that difference. If you're a person moving, so you have 0, 45, 90 degrees, angles smaller than that, for the overall optimization wouldn't really make a difference. And this is what we have. So, yes.
You have a technique for accounting for outliers when you have the measurements and then you do the weighted least square, but you have one outlier and it's not tested.
So we did that for the step length because this happens in the step length estimation. Sometimes one person, you're standing in your place and you're doing this. So it's kind of, it generates acceleration, but you're practically not moving. So we did some form of removing outliers or unexpected measurements in the step length. We didn't do that for the angle. But the only thing I would say is that, so you in the phone you have basically two sources of measuring the angle, the gyroscope, and we still have the magnetometer, the compass. And a lot of algorithms can use just the compass to provide the absolute heading. The problem is with compass measurements inside buildings, there's always a bias. All the electronic devices, the building structure, we ended up always with a bias that goes up to plus or minus 30 degrees, for example. So the point is, so when we got the heading measurements, we correlated between what you get from the magnetometer and the gyroscope. As long as they're both close, or the transitions are close, that somehow makes sense that you're getting correct measurements from both. But if you end up with, you don't have a very high correlation between the measurements, that is an indication that there's some error in the measurements. So this is true trajectory. We used the start and end point as a loop closure. So we know that you started and you came back here. The red line is what you get from just applying PDR without any calibration. The green is with calibration. It's somehow rotated back, but not as much. And this is what you get with GraphSLAM, with optimizing over the old trajectory and using the loop closure at the beginning of it. And to further see what happens with landmarks, we added here fixed positions. So you know you're here, you know this is what this is. It just adds more constraints to the problem. So mostly you end up with a better approximation, but it really depends on how you walk and where the landmarks are. To try and provide a quantitative measurement of how the trajectories are better, this is an example of some measurements. We used what is called as trajectory similarity measures. These are very common in a lot of computer science applications used for traffic patterns and planning vehicle traffic and pedestrians, tracking animals' migration. So you're trying to detect the trajectories that are closer to each other. And these are two measures: dynamic time warping, which in this case could be used to provide an average error per position, and longest common subsequence, which provides a percentage of how many of the estimated positions are within a specific threshold from the actual trajectory. So these are for two different trajectories, two different durations. You see how the error goes from, so this is the error just with PDR, this is the error with GraphSLAM. This is what happens with calibration. And finally, we add, just to see how the landmarks make a difference in the analysis. And mainly, GraphSLAM always performs better. Calibration might or might not be, but using GraphSLAM always performs better. Landmarks is relative because at this specific example, you see that the average error is less, but the number of points within 1 meter is the same. Within 2 meters is the same. The number of points within 1 meter actually less. So what happens in the optimization problem, it overall, the further points get closer, but the close points somehow moved within 1 meter to within 2 meters. And this concludes the first part. So, Dad, any questions? At the end, here?
It's like part one, right?
Yes. Okay. So, the next part is, yes.
So when you're saying landmarks, how is this physically incorporated in what you're doing? I'm thinking you went to one part of the building and decided that that was a landmark. Right?
So,
how do you put
for
that?
this specific simulation, it was you saying that I am here. I know I'm here.
Gotcha.
It should be done automatically. or I mean, either you expect people to say that they're here, or you expect that there is like a beacon, maybe a Bluetooth device or something, which somehow what we didn't want to go for, because again, this means that you have infrastructure known, like you know that there are Bluetooth beacons inside the building. Another way is using what, Brian?
I was saying, if you get close to a window.
Yes, you can, some activities, and actually this is what Tad did some work about before, using user activity as landmarks. So going down the stairs, I can figure out that this is a stair, so this is a landmark. So if I'll come back again, this is a stair. Or so suggestions have been made for stairs, elevators, and some user activities, other activities. But this is actually what motivated the second part, is that we want to have some form of more constraints to the problem, but we don't want to depend on the building infrastructure. So the second part is that we try to, instead of using landmarks, we have many people walking in the building, and based on their interactions, we can use their proximity as constraints. So using Bluetooth. So of course, the idea of using Bluetooth is everywhere. Every mobile phone has Bluetooth. Every smartphone has Bluetooth. 90% of mobile phones all over the world has Bluetooth. Bluetooth Low Energy was released with Bluetooth 4. It's now on every smartphone. It's just made for short burst data transmissions with very low energy, very low power. Bluetooth Low Energy, it enabled a mode for Bluetooth, which is a broadcasting mode. So each device periodically transmits a unique ID and some information about itself. And usually Bluetooth transmits within the same, band as Wi-Fi. There are 40 channels for Bluetooth, but the broadcasting happens only on 3 channels, which located strategically so that they have minimal interference with Wi-Fi. So using this, we developed an app, again with the help of Tad, who volunteered his phone and his time to do that. So a Bluetooth app. So app, basically what it does is that it advertises the phone with a unique ID, and at the same time it scans for other smartphones around you that use the same app or have a specific ID. And then when the phone detects another phone that has the same app installed, it records the timestamp, the phone ID, the RSS, which is the major point here, the received signal strength from the other device, and then uploads that to a server, and then we process the data. And the whole idea is using the received signal strength between phones so we can determine how close they are to each other, and then use this as a constraint to the problem, instead of needing landmarks. In order to do that, we needed to somehow provide a model for Bluetooth measurements. RSS, received signal strength. So again, we did some experiments. The first set was static, so just 2 phones, 1 meter, 2 meters, 3 meters apart. We calculated the received signal strength, and this is the histogram of the received values between the 2 phones. 1 meter, 2 meter, 3 meter. As you can see, although there is a trend somehow that as you go further, the received signal strength drops, but still the received signal strength values are not a good indicator to directly calculate a distance between the 2 phones. It's very variable, and actually some paper actually just demonstrated a lot of surveys just to say that you cannot depend on just RSS to detect distance. The other set of measurements, again, so dynamic experiments, 2 people walking around, yes.
Do you have a sense of how much of that's due to the antenna orientation? When you did your measurements, I'm imagining you kept a constant orientation of the phone,
yes.
so the antennas were the same,
yes.
always pointing in the same direction.
So a big part of the problem, actually, that you mentioned it, is from the phone transmits periodically on the 3 channels, and so they have different frequencies, so they somehow have different frequency responses. So the received signal strength from from each channel is different, and the phone, at least the iPhones, cannot differentiate the received signal from which channel from the same phone. I think that Androids might be able to do that, but not the iPhones. So it's basically receiving 3 different signals from the same device. And then, of course, you have the multipath problem inside the building. But this is a big part of the problem.
So you you say RSS, do you mean RSSI?
RSS, dBm value.
Yeah, sure. It's dBm value. But
Yes.
how are you measuring it?
So the newer Bluetooth editions allow that. The previous ones would give you an RSSI, an indicator in which it's a range of whether you're into range or out. The Bluetooth 4 and Bluetooth low energy actually give you an RSS estimation in dBm. Okay, so two people. This is me. This is Aiden. He's not here today. Walking around the building, and we're crossing paths twice, and we see the received signal strength in time at one of the phones from the other one, and you can see that there is detected two peaks at the timestamps where the users were the closest, and so we proposed that instead of using the RSS values to give us a measure of an absolute distance between the users, we can use the values as a constraint to the optimization problem. So instead of saying if the phone receives minus 40 dBm, that means he's 1 meter away from the other user, we can say that it's less than 1 meter away from the other user, or less than 2 meters, based on the threshold of the distance. So basically, including this measure into the optimization problem, we would have the same problem as we had before, it just be a constrained linear least squares problem. These constraints, so we format a joint optimization. We're trying to optimize both movement trajectories in both users, and we add constraints at the time instance where the users receive peaks of RSS above a certain threshold. And these points we can add here as a limitation of where the points are as relative to each other. Using that, let's see an example. So again, two trajectories, one starting from here, the other starting from there. This is what we get from PDR, and the highlighted points, the highlighted positions are corresponding to the time instance where the phones receive maximum peak RSS from each other above a certain threshold. I need to say above a certain, because the peak is smaller than we exclude that. And this is what happens with calibration, and then this is the joint optimization, where you can see how the distance is built. Yes?
Do you see any waveguide effect inside the building? Does that
What?
affect the waveguide effect?
I'm so sorry.
The waveguide effect inside the buildings.
The wave.
It's a common phenomenon where because you're inside the building,
I can't hear the other word.
the
Say-
waveguide effect.
The waveguide. We didn't study that.
No, I mean, essentially what happens is your signal is supposed to be coming to the path loss minus 40 dBm, but because of constructor interference, you would actually see it as minus 25.
Yes.
So you get false alarms, and that would affect, you think that
So-
you're closer, but you're not, and that would start.
So this is why first we set the threshold based on a lot of measurements within the building, so it's a real threshold. And number two, we made the threshold really high, so we're trying to maintain a very I want a minimum false alarm. It's better to lose points than I have points that are not close to each other. So I get the threshold set pretty high that I need to make sure that they're really close, as best as could be. Okay, and if we again look at numbers, we got pretty good results for both users simultaneously. The arrow went down again to about 1 meter, and the number of points really close to the two trajectories increased, again using GraphSLAM versus PDR and PDR with hidden detection. And this is the second part. Finally, I just have one more slide, which is, so after you have the older trajectories, how we can use them for locating other users, or location actually for the same user or other users. So getting the movement trajectories creates some form of a topological map for the building. You have a sequence of the most probable locations of users inside the building. And so if another user is walking inside the building, or the same user later on, and they can track and store their own trajectories for a time period, either through PDR or any other way, we can use these trajectories to actually detect where the person is. And this is just one example of maybe how to do that. So the green line is previously detected trajectories. These are two different examples. If a user is moving in the building and they somehow they can drag their own trajectory, then we can match this with the actual with the trajectories that I stored before. It somehow it becomes a pattern recognition problem, and that's one way of looking at it. You can use we use trajectory matching. We use neural networks for it, and so just by map matching techniques, you can actually use that to detect where the person is with much higher accuracy. But this would be another topic. And this concludes my presentation.